fearless engineers. They get credit for building the largest computer chip in history. How big is it? The size of a dinner plate. That's one piece of the puzzle for the hardware that drives big data. Some other pieces include the storage layer and those mission critical compilers.
The future is here already. It's just not evenly distributed. Yet. Today's world teems with innovation. The nexus of hardware, software, and human ingenuity promises a revolution in possibilities. What does tomorrow look like? Witness Future Proof.
Your host here, Eric Kavanagh, and I'm already excited, folks. We were just chit-chatting in the pre-show, off to the races here. We're going to talk about the hardware and also other aspects of big data that runs the show here and why that stuff matters, why these platforms matter. I've got several experts on the call for you today. We've got Shivek from Compiler Works. We've got our old buddy David Friend from Wasabi, and our other new friend, Andrew Feldman from Cerebrus Systems. We're going to talk all about what's going on here. And I'm just fascinated by something called compilers. So we were just talking with Shivek in the pre-show banter here about what these things are. So just to explain to our audience out there, when you write code, you write it in various languages, and then you have to compile it to run on a platform. So historically, that's been Windows or Mac OS, for example, Android. These are the platforms, but also the clouds like Amazon, Microsoft Azure, Google Cloud Platform. These are platforms where you have to compile the code to run. Well, the compiler is really the key component here. Like without it doing its job properly, nothing's going to work. And people like to run in their own languages. They like to use Python or R or whatever the case may be, C#, C++, Go. There's lots and lots of languages out there. In fact, someone did the math a while ago and realized there are more computer languages now than there are human languages in the world. So that should give you something to think about here. And languages are very different. They have different ways of doing things, just in the way that human languages are different. I learned years ago that Italian is not just a different language, different words for the same things. There are different constructs in the language for how you even conceive of things and explain things. And so one language to another is very, very different. And the same holds true for programming. And with that, let's jump right in and bring in Shivek. You had me just taking notes here, thinking about compilers and what you do. So just very quickly explain to our audience who you are and what you do for a living.
So I'm Shivek, I'm CTO of Compiler Works, which means I'm technical lead for the principles and implementation. What we do for a living is we solve data integration problems. We have a suite of compilers which understand many of the enterprise data processing languages on the planet. And we can do two fundamental things with these languages. One, we can turn one of these languages into another of these languages. And two, we can tell you what you need to know about your code written in one of these languages. So turning one language into another is, I am on legacy platform. I want to be on modern platform because it's cheaper, faster, more appropriate to my business purposes. And the other side of it, the what do I need to know about this code is, hi, I've got 10 million lines of code. Does this code violate any of a number of financial or data protection laws? If so, where and when, and what can I do to resolve that?
Mm-hmm. That's a huge deal. You were saying in the pre-call that for some of these financial services clients, they're not allowed to touch the code manually. They can only touch the code through automated systems, which, I mean, in a way makes sense. But in another way, I mean, I'm nowhere near as well educated on compilers as you are, obviously. But I used to play a little joke with myself, and just to show off to people. Years ago, I would launch Microsoft Word, and I would type "Hello World," and then I would do save as HTML and load that in a text editor, and it's like 5 pages of copy. It's like all these commands, like all this stuff. You're like, what? Like, why do I need all that? And that's sort of like, I mean, it's somewhat analogous to what you're talking about, right? That you have to compile the code to run on that particular platform. The platforms change, so you have to update the compiled code, right? But what do you think about all that?
I mean, one of the significant challenges when you're doing a migration rather than a straight up compile, say you're trying to do a platform modernization onto a cloud platform, is that you have a customer who is now going to maintain their code on that target platform. Mm-hmm. And so we actually can't do the thing where you generate 5 pages of code out of Hello World. One of the harder problems that we solve is that we have to generate code for a target platform, which is short, elegant, optimal, idiomatic, follows all of the vendor's guidelines, because that code is henceforth going to have to be maintained by a human. And in fact, the sort of compilers that we mostly end up writing have a lot of differences from the classic compilers that you would consider. One of them being that we're not guaranteed correct input. If somebody's doing a platform modernization because they want to process on a modern big data platform, they give you their code. There's 10 million lines of it. Probably 70% of this code is correct and complete. You're missing 20 to 30% of the definitions. The customer still wants the job done. Right. So now you end up with a compiler with a much, much more interesting type checker, various sorts of heuristic engines, various sorts of static analysis routines, which are basically designed to figure out how to help the customer do a successful migration to a target platform when what they've given you at the source is not perfect. Writing a simple compiler basically is an academic project. Any postgraduate can write a compiler that takes a language and compiles it down to a target system where the language was appropriate for the target system. But what we have to do as a daily matter is to take a piece of code that was written in a variety of languages and compile them to a different target system where the languages were not physically suited for that target system. And that, I think, is where this gets really interesting. Do so in the presence of multiple errors and incompletenesses.
And so when that's done, like when you get one of these jobs, someone wants to migrate from, let's say, a traditional data integration platform to one of the new cloud-based environments. And there are lots, I mean, there are tons of companies these days doing high-powered data ingest, data movement, companies like Equalum, StreamSets. There are like a dozen of them. They came out of nowhere. Fiverr, all these different companies are just collecting massive amounts of data and moving it somewhere else, right? Data orchestration is a term used to describe that. What does that process look like? I mean, do you basically take the code and can you dynamically assess how much of it you have and then get sort of a report of where you don't have definitions of things? And then you have to kind of manually go through and manage all the exceptions? How does that work?
Yes, absolutely, except that you don't have to go through and manually manage all of the exceptions. What our compilers do is internally we treat them as they do the job that a human would do under the same circumstances, which is where they have complete information, they do a complete job. Where they have partial information, they make valid assumptions based on what else they can glean about the code base and do a partial job. But the moment you say, okay, you have to manage the exceptions in a 10 million line code base, you're dead in the water. The objective here is to do the job, to do the migration, to bring as much value as you can. And so in terms of actually doing a migration, somebody comes in with legacy platform A and you say, okay, I want to go to target platform B. The first thing that you'll do is you'll qualify the actual workload against the target platform, because there are certain workloads that just don't work for certain target platforms. You know, there are things to do with relational algebra that you just can't do on a streaming platform. And then having done that, what you tend to find is that platforms break down approximately into groups. And then our compilers have the ability to compile the source code into a full semantic model. We're actually really a computer algebra company. And then the computer algebra engine's job then is to work out how to do the customer's job within the semantic limitations of the target platform. And this is actually where the modernization aspect comes in, because a lot of the old platforms were designed to be all things to all people. If you bought platform X in the old world, your problem was solved. It might cost you 10, 20, $100 million a year, but it was their job to solve your platform. They didn't specialize. And then you go to the new platform where they'll say, you know, you cannot have the following operators. You can do streaming operators. You can do relational operators, but you can't do indexing. You can't have a sequence or whatever. And the computer algebra engine's job then is to work out how to fit the required semantics of the job into those restrictions. And then having done that, the remaining problem is now, okay, express that restricted semantics in terms of the actual text that the target platform needs, whether that's StreamSet API or BigQuery SQL or whatever it is. And then the last job is simplify that, condense that, make that maintainable, make that human readable. And then you deliver that to your end customer to say, here is your legacy code running on the new platform. It's elegant, it's minimal, it's performant, it satisfies all of the vendor's best practices. You can now go ahead with your migration and maintain it.
That's fascinating. How'd you get into this business? How did you start doing this?
Accident. I have a great interest in.
You didn't grow up dreaming of being a compiler engineer?
I'm not sure what I grew up. I think I fell into it by accident. You take enough things apart and you work out how they work inside. And I think that the best analogy I use for compilers is if you're sitting at a pool table and I give you a ball, most people can roll it into a pocket on the first shot. Fewer people can hit the ball with another ball such that the second ball rolls into a pocket. But now if I tell you you're not allowed to hit the first ball yourself, you have to hit it with a stick. That's kind of what compilers is like, because you're writing the code which implements the compiler, which manipulates the target code that sees the data. And when you get a bug report back from the customer that says that, the result was 15.4 and it should have been 15.38, and then working your way backwards up the snooker balls all the way to the pool cue to work out where the issue was in the code generation in some binary mode where you generated not quite the right sort of rounding operator, that's the thing that holds people back from being able to be compiler engineers. It's the thinking thinking at two levels of abstraction, not just one.
Yeah. Now this is fascinating. And so in terms of the platforms, do you then work with those companies to get schematics of what's inside? Do they provide documentation to you in some form of electronic format such that you can map things out, or how does that work?
It's a mixture. On the whole, generally, yes, because typically if we're working with a vendor, it's very pleasant to work with them for support. A lot of stuff is not defined. It's defined by the behavior of the language. I think if we go back in history, I think Algol was the first language for which it was proved that a compiler could actually be written. And I think that almost all modern languages have a case where they say, if you do the following, the behavior is undefined. And one of the things that we really stress to developers is that, the JVM is very well studied platform. And they say, if you do these operations on separate threads, the behavior is undefined. And a lot of beginner programmers look at that and they say, well, the behavior is undefined, but it's either 1 or 2. But it isn't. It's either 1, it's 2, or it eats your cat. Because when they say undefined, what they mean is all bets are off. And so the answer to your question is that actually the documentation for most platforms is an approximate, incomplete and partial guide to what the platform might do under certain circumstances if it passes its own test cases.
That's right.
And there are platforms where I think we know more about them than the vendors
I believe
do.
that. I believe that's true. I think that's really important to comment on as well, because as you suggest, and again, to share with our audience here, right? Developers, especially from the sort of beginning of DevOps until now, I think developers have just been hurtling forward, doing all kind of cool stuff. And that's what developers want to do. They want to create things, they want to get stuff working, and then move on to the next thing. They don't want to do documentation of anything, which is why you want to have dynamic documentation, right? That's one of the, there's a company, Warescape, that got bought by Idera, and they focused on automating the documentation of what you're doing. So you don't have to worry about that. But a lot of places don't have that. And just thinking like instructions for how to use a tool from a software company, you'll Google it. And unless they're very clever about SEO and about how they manage those documents, you may find instructions from last year or 2 years ago or 3 years ago, go to file and then go to this menu, and it's not there. What are they talking about? That's because it's hard to keep up with that stuff, right, Shabbat?
But you also have to bear in mind that these people's job is not building languages. These people's job is processing your data. And so if you come to them and you say, here is a check for some money, process my data. And they say that if you write the following string in this language, it will do the thing you asked for. It's not their job to think about all of the other consequences. So in this sense, migrating to a platform is easy because you can go to the vendor and you can say, I need to produce the following effect. And they'll say, this piece of text will produce that effect. If you're migrating off a platform, it's a nightmare. Because what you'll find, and it's very common, I can name you several billion-dollar vendors, multi-billion-dollar vendors, where it is very common for people to use operators on their platform, where the manual officially says, this operation is undefined, do not use it. But everybody uses it because in practice, everybody knows what it does.
Wow.
And that's when it gets really hairy, because these people are not They're not language designers. It's not their job to be language designers. We don't expect them to be language designers. But if we as a company are facing a customer who say, move us from legacy platform A to target platform B, or people who say, here is 1 million lines of code on target platform, tell us whether it contains a protected information violation, we can't go back to them and say this operator is undefined. They just come to us and say, well, figure it out, answer the question. We run this operation every day. This is what it does. And this is why we have to be more experts in the language even than the vendors of the platforms, because the customers just pay us to do the job.
Talking all things compilers and hardware. We were hinting at hardware. Now we're talking to the compilers because, again, you write software that must be compiled to run on a platform. Well, part of the platform is the hardware that they're using. Now, virtual machines have been around forever. JVMs have been around forever. Kubernetes is a new entity, relatively new, that is pretty fascinating stuff that Google came along and did. I had a really funny story about why Kubernetes won over Docker, because Docker came up with the idea first. And the person told me that, yeah, the reason is because Docker wanted to charge developers for the platform, and developers don't like to pay anything. I thought that was kind of funny.
Not for software.
Not for themselves, right? They build it. You don't buy these solutions. You build it from the ground up every time. But there was Andrew Feldman in the background joking, and his company has fearless engineers who build these massive wafers to be able to do massive scale of processing. Right, Andrew?
We do. My name's Andrew. I'm CEO and one of the founders of Cerebra Systems. We build a new type of computer for AI work. And our decision to build the largest chip ever made, a chip that's approximately 56 times larger than anybody had ever attempted, was to bring a huge amount of compute resources onto a single piece of silicon. And so in our latest chip, a 7-nanometer part, we have 850,000 cores.
Wow.
We have 40 gig of on-chip memory. And so, to give you an idea, we're 56 times larger with 1,000 times more memory than a graphics processing unit. And we do this because in AI work, big chips process information more quickly and produce answers in less time. Mm-hmm. And that's the goal in AI work. And so in a big data discussion, we fit in the artificial intelligence portion. And in a compiler discussion, we had to write our own compiler. And we had to write our own compiler because the powers that be in the artificial intelligence world, they drove the community to write in one of two languages, both Python-based. One is called TensorFlow and one is called PyTorch. And that was a big step forward for our industry. We moved to a spot where you could move those languages across any hardware platform. And so when we decided to build a company, we knew that these languages were the way the practitioner would program our machine. But we didn't want the programmer to ever have to worry about architectural decisions we made in the hardware. And so between the programmer trying to describe what they want the neural network to do, and this massively parallel machine, the fastest machine for AI ever built, lives the compiler. And what the compiler does is it takes in their intent and converts it into an extremely fast set of executable blocks that are then placed on our giant chip and then run. And the result is we just did a project for a large pharma company, and work that was taking 180 days, we were able to do in 3 days.
Yeah, and so let me explain why this is so interesting. Because what happened in the world of a big compute, of big data, if you will, is as Shevek mentioned, we went down this road of massive parallel processing, right? Take a problem that you want to slice and dice data, you want to run a particular algorithm against this set of data. Well, split that up into 100 or 1,000 or whatever, how many ever nodes you have, or cores on nodes, et cetera, and just tackle it all at once, right? But what's interesting is that you took a different approach. You're like, well, what about just creating a big honking processor and just big wafer that can do all kinds of this stuff by itself? So you don't have to scale out, because there are network, there are bandwidth issues that come along with MPP. There are all sorts of little tricks that you have to learn or to avoid if you're going to go MPP. And the key here is how quickly you can get answers to your questions, right? Because that really dictates what's possible in terms of the human computer data interaction of getting answers to things. And what happens that I've seen is that people get accustomed to their speed of query and they kind of work around that. In other words, they're doing queries that take too long, they just go on and do some other query. Like it's too much of an impediment. And so what you're doing is really significantly raising the throughput capability of a single machine. Is that right?
Dramatically. I think in the artificial intelligence world, if you have to do a piece of work, whether it's a simulation or whether it's an artificial intelligence workload, and it takes 4 months to do the work on a big cluster of machines, you're not going to do that work very often. Mm-hmm. The number of ideas you can have, the number of iterations you can run will be very few. If you're a graduate student, you might do 2, right? Mm-hmm. you plan for it for 4 months, you run it for 4 months, you do analysis for 4 months.
That's a year.
It's taken forever. That's a year. You just lost a year.
Right.
If instead it takes 3 days, or if instead you can do it over lunch, right? You might do thousands of those iterations, each time making modifications and improvements. And while those iterations are running in the background, you're constantly getting new data, new results. And so for artificial intelligence work, which is sort of where we play, the amount of time it takes to do this analysis, to do the equivalent of a query, to train a neural network model, this is what we're trying to reduce. And if it takes huge amounts of time, only a few people can do it. Only the Googles or the Facebooks or the OpenAIs can do it. Everybody else can't do it. And it doesn't get done very often. And so by radically reducing the amount of time it takes to do this work, we open up the field to more innovation, to more ideas, to more iterations. Mm-hmm. And I think that's one of the joys.
Yeah, no, it's fascinating stuff. And so and a lot of people don't realize, but in the life sciences in particular, HPC, high performance computing, has been around for a long time because it kind of had to be. I mean, if you're working on genomes and things of this nature, you've got entities that have tens of thousands of characteristics, and you can just do the math, multiply 10,000 by 10,000 by 10,000 by 10,000, and suddenly you've got a pretty complex problem that you're trying to ask these processors to crunch through. And so by opening that floodgate of processing capability, you're just dramatically changing the dynamics of how AI gets designed, gets managed, gets run. Because to your point, you have to plan and you have to do it, then you have to understand what you did, then you send it to production. I mean, this is a pretty long cycle. So you're collapsing what was a huge chunk of time into a very small period of time. And I'm guessing you've just got, I don't know how many clients, but can you talk about how you sell something like that? Because you have to get a whole ecosystem around your new chip, right?
We sell a computer system. So the chip goes in a system we make, and we wrote the compiler. And so a big customer of ours is GlaxoSmithKline, and we deliver to their premise a computer. And they begin taking their code that they wrote for graphics processing units, and with a single line of code, it's roughly, estimator equals CS estimator. We can run all their code.
Wow.
And work that was taking months is done in hours. And I think once that happens, it's not like they stop and have a coffee. They say, we had this huge backlog of ideas.
Right.
That we weren't able to test.
Wow.
Right? We had this giant backlog of things we wanted to do.
That's so cool.
We didn't have the time to get it done. And so the ideas start flowing through, and suddenly the bottleneck is no longer the compute resources, but it's the creativity of the AI practitioner. Suddenly it's the creativity of the data scientist that is the limiting factor. And that's where we want these to be, right? We want, whether it's a compiler or whether it's new hardware, we want the the limit not to be the infrastructure.
Right.
We want it to be the coder, the ideas they have, the thinking, and we want to build infrastructure so that their ideas can take flight. And that's really what we do.
Yeah, that's fantastic. This is really cool stuff. Well, let's bring in our final guest before it's too late. We've got David Friend out there from Wasabi. There's another guy that's been around for a while and been pretty clever about writing code to store data. I know a lot about Wasabi from a past life working with these guys, but David, you guys got a bunch of money recently, and of course you are providing cloud storage. So you're allowing people to persist their data at a much lower cost, I think, than some of the other competitors out there, and even a faster speed. Tell us a bit about what you're doing these days and what you think about our lineup today.
Yeah, I mean, we designed Wasabi to be plug compatible with Amazon S3, and our costs are about $6 a terabyte per month versus about $23 a terabyte per month for Amazon S3. And by most benchmarks, we're considerably faster as well. And we spent 11 years at Carbonite learning how to do cloud storage really well. And so we're cloud storage experts. We get down there and control the movement of the heads on the disk drives and all that kind of stuff in order to pack data more efficiently on disk and that sort of thing. And it's really interesting to see the AI applications. We have about 23,000 customers today, and probably about 10-15% of them are AI related applications where people are I was just looking at one today. We store the data for one of these big telescopes down in Chile. And, they have an AI application that's looking for exoplanets. And, so they're looking at, I don't know, thousands, maybe millions of stars every night to see if anybody's changing their brightness. And, so that takes a lot of processing. And, we store a lot of data for some of the big hospitals, the big teaching hospitals particularly. Including Harvard right here in town. And, it's amazing to me, people are always finding ways to analyze medical imaging in a way that, they're now finding that they can write algorithms, AI algorithms that will detect cancers faster than a human radiologist. Mm-hmm. And, to do that, they need a huge history of data because, by the time they finally do diagnose somebody, they want to go back and they want to look at the x-rays from 2 years ago, 5 years ago, 10 years ago to see if somebody missed something, if there was really something there that could have been detected. And so, we're seeing these data lakes just grow and grow and grow. And I was looking at our AI customers, what we think are all of our AI customers, and their data grew 60% year over year organically, just the same data sets over the last year. So, we're always getting new ones, obviously, but just the ones that were there last year and the year before that, have been growing on average. I think it was about 61%. Year over year.
That's a lot. Yeah.
Yep. And we have people in the, obviously the Wall Street people. One of our customers is called May Street, and they collect all of the exchanges, all of the transactions that take place on all the world's major stock exchanges in great detail, this down to the second of the transaction and so forth. And it's amazing how much use that gets. I mean, they probably sell that data to most of the major banks, investment banks worldwide, and they're constantly creating, trying to figure out ways that, they can go back and regression test new algorithms for how to skim a couple of crumbs off the table as these transactions pass by.
It's not so, Dave.
Well, folks, what a fantastic show today. Look these folks up online. Shevek, it's Compiler Works. Is that right, the company?
Yes.
Compiler Works, his compilers work. Apparently, David Friend of Wasabi and Andrew Feldman of Cerberus Systems. Great stuff. We'll talk to you next time, folks.